Okay, according to this, it is noon o'clock. I'm just going to give everyone a few minutes to come on in. Trying to get the auto exposure to behave. All right, well, let's get this started. Welcome, tech art enthusiasts. Welcome to another episode of Tech Art Talk Live. I am Chris. I will be your host for today's session. And today we are going to be discussing linear algebra. Linear algebra is probably one of the most important, I think it is, the most important of all of the mathematics that tech artists probably need to understand in order to get their job done. But honestly, linear algebra is a huge topic. And so a lot of folks are going, how do I learn linear algebra overnight? It's a huge topic. What do I need to know? Well, that's what today's lecture is all about. We are going to be discussing linear algebra. So without ado, let's get things started. All right. So I call this linear algebra light because, as I mentioned before, linear algebra is kind of a big topic, and it's kind of a topic that is kind of consuming, but we wouldn't be able to do computer graphics without it. So what is linear algebra? Anyway, linear algebra, come on, let's get going. You can work for me. Yes, it is a branch of mathematics, and there's concerning a system of linear equations. Now, this concept itself of linear equations might be a little bit funky and a little bit nutty and a little bit weird, but suppose if you, well, just say that it's needed if you're solving a whole bunch of algebra all at once, then that is a system of linear equations, and it's represented in vectors and matrices, and that's what's going to be today's lecture primarily composed is vectors and matrices. And it's present in almost all areas of math, but it's very important for dealing with geometry, especially when dealing with planes, rotations, and lines. All right. Okay, when dealing with geometry, it's more, okay, linear algebra here, in the context of computer graphics, is more of a subfield than the actual true representation of linear algebra. So it's kind of like I said, more about this linear algebra light business. Now, as a tech artist, what will it help me with? That's probably what you're probably figuring out. It's like, do I got to spend all this time learning linear algebra? And it's a little bit like knowing C++ or calculus. Will those help you as a technical artist? And the honest truth is, at the beginning of your career, it's not going to help you a lot. However, as most technical artists find after they've been in the business from 3 to 5 years, and possibly even longer, that they hit a glass ceiling and they can't progress. And a strong understanding of linear algebra, just like C++ or calculus, might just be able to be the trigger that helps you smash through that glass ceiling. All right. Ultimately, the more linear algebra that you know, the further you can go. And by hands down, the best technical artists, especially those involved with either rigging and or rendering, have the strongest grasp of these concepts of linear algebra. So actually, how much do you need to know? Okay, well, buckle yourself up in, Dorothy. We're going to go for a ride. All right, so what is a vector? A vector is a one-dimensional array representing a solution of a system of linear equations. Okay, yeah, we all got that. That's kind of abstract. It's an element of the real Cartesian space R of n. What in goody go-go's does that mean? Okay, well, that's math speak, meaning that a vector can be any dimension. That means it could be of one dimension, I mean, one object. It could be 3, that means like X, Y, Z, red, green, and blue, or it can even be 20 dimensions big. Now, what are you going to do with those 20 dimensions? I haven't the foggiest idea, but they're there if you want to use them. And it's an explicit representation of an element of any abstract vector space. Yeah. Okay, that's what okay, those last two ones, that's talking, they can be any size that you want. All right, now as a tech artist, we deal mostly with velocities, forces, and directions. And that's what we're going to notice that in this diagram here, that all these vectors, which are denoted by the yellow arrows, are originating from the origin. All vectors are basically parallel. You know, they're like an infinite number of vectors all over the place, but they are best observed when coming from the origin, because the origin is really the understanding of where they are actually coming from. Now, a vector can also be a point in space. And here, it's a two-dimensional point in space where we have the position 4, 5. If we go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, in this position in space, so this vector 4, 5 represents the two-dimensional space of this vertex in two-dimensional space. Now, a vertex can also be a color, or I'm calling it an n-tuple. So in this situation, it is a 3-tuple. In this situation, it is kind of like a kind of like a reddish pinkish kind of color. I suppose there's a proper word for it, but the term isn't really coming to my mind. Now, the notation wise, you can list your vectors either vertically or horizontal as rows or as columns, but they're pretty much designated always by square brackets. And often they have the special component listed as a little sub number underneath them. But also they are listed as these vectors are listed as with a variable name, but with an arrow on top, and that's just to mean it's a vector without having to go through and write all the contents on there. This isn't a standard. This is just something that's used. So really, it's either vertically or horizontal. That is the kind of representation of the vector in square brackets. Now, for technical art, this is the typical convention. Unless you're dealing with colors, what you're probably dealing with, quote unquote, you're dealing with coordinates in homogeneous space. What does that mean? So that means is that you're dealing with a 1x4 matrix or a 4x1 matrix, and you're dealing with a value of x, y, z, and w, and that's horizontal and vertical. Now, some of you might be going, okay, what in goody goo goo are you talking about with this w component? Okay, this is what it's called being in homogeneous coordinates, and without going into too deep with the whole linear algebra business, let me just tell you that when you're dealing with homogeneous coordinates, the w value of 0 means that the vector is a direction. If the value is a 1, that means you're dealing with a point in space. Now, this actually comes into a very important thing when we get to transformations. Now, if it's only a 3-dimensional vector, x, y, z, and the w value is not present, it is understood that if the w value is not present, it's understood and it has a value of 0. So therefore, the vector is considered by default a direction. Okay, now you can, okay, let me go, and I actually have some demo action here to show you guys a little bit of, oops, we don't want to see the subtraction yet. All right, so we've got a little bit of Houdini here, and what I want to do is pull up, I have this little vector calculator that I created. There we go. We have this vector A, and here's the direction of this vector. It's x, y, and z components, and this is its w component. And remember, if the w component is 0, it is a direction. And now this is its magnitude, and there you go. You see it's pointed in the positive x, y, and negative z directions. Now, if we wanted to get with this, we've got another alternative vector. I've got vector b. Now it's hanging out over here, Now it's going into the negative x, positive y, and negative z direction. And it also has a w value of 0 because it's only dealing with a direction. All right, so suppose we wanted to go ahead and add these two vectors. We've got vector A and vector B. Now what if we wanted to go ahead and add these two bad boys? What would we have to do? Well, addition of vectors is done simply by adding the corresponding components. So you would add ax plus bx, you'd get ay and by, and then az and then bz, and those would be your brand new components. Let's see what that would actually look like in Houdini. I'm going to go ahead and get rid of this. Hello. All right, so I'm going to go ahead and add addition those. Okay, so here we have vector A is written by the magenta, B is in yellow, and if we now see AB is the addition of corresponding components to each other. Now, as you can see, the culmination, since they're kind of A and B are kind of going in the same direction, which is in the negative z direction, they kind of like amplify each other in the negative z direction. Now, what I like to look at is when you look at two vectors in a kind of like orthogonal perspective, like from perspective from this, if you were to take vector A and then add vector B onto it all the way from here, you would get the result vector C. All right, so that is how you do addition. So let's focus on how you do subtraction. Now, subtraction is basically the exact same operation, but kind of like done with subtraction. So you would have ax minus bx, ay minus by, and az minus bz. Now, mind you, this is not a commutative operation. That means it doesn't go in both directions. A minus b does not equal b minus a. And we're going to get to see why in just a minute here. We've got these two vectors here. Now, what if we wanted to subtract a minus b instead of a plus b? Come on, click away. There we go. As you can see, the results are radically different. And they're usually, okay, yeah, they're much different. So we had vector A in magenta, vector B in yellow, and A minus B, vector C, is going off in red in a completely opposite direction. Now, it kind of makes sense is that what I like to think is, for me, subtraction is a little bit hard to understand, at least from this perspective. What I like to try to do is say, okay, if I was to go vector A and then I was to go in the negative B direction and actually go in the negative B direction, this is the result I would get of A minus B. Okay, so a little calculator, vector calculator like this is actually helpful to help understand these critters. All right, scalar multiplication. Now this is, notice that you have a float scalar and then we're going to be multiplying it by a vector, and then you just take that float scalar and then you multiply every individual component by that float. So vector C now equals the value of 2, which is your scalar value, times ax times ay times az. So it's 2 times ax, 2 times ay, 2 times az. And that basically scales the vector either forward or backwards depending on its length. Now visually, it's a little bit confusing. So I'm going to go ahead and take vector A and then multiply it by 2. Now here we have it there, A multiplied by 2, and which is okay, but notice here that when we have just put vector A here, it kind of like sits on top of each other. And so it's a little bit hard to see, but notice that really 2 times A just really expands that vector to at least twice its length. And if you were to have it, it would cut in size by 1/2. Okay, now the length. The length as we, if you all know what the Pythagorean theorem is, that's ax plus a squared plus b squared plus c squared. You take the square root of that, and then you get the length of the hypotenuse. Well, that works very well for vectors just the same, and that's exactly what we're doing, is that we take the square root of the x component, the x component squared, the y component squared, and the z component squared. You add all those up, take the square root of that, and you get the length. And let me get rid of this because it's kind of annoying. But the connotation for the vector length is when you've got these little double bars, the double horizontal bars there, and it says that going from here to there, this vector is of length 0.94, which is almost 1, which is kind of important. So this is all good and fine. You have this vector length. This is knowing the vector length is often equivalent called knowing the vector's magnitude, which is very, very important when you're doing visual effects. And when you're doing visual effects, you're dealing with forces and accelerations, and knowing the acceleration or force when it's represented as a vector, and then having the vector length as its magnitude is really, really important. So that's another use of it. So what other uses do you use for the length in there? Well, a unit vector is a vector of length 1. Now, vector A that we were dealing with, this is almost length 1. But the unit vector is good for when you want only the direction. So if you only want a direction and you don't really care about magnitude too much, unit vectors are really good. Okay, now when you're dealing with shader programming, you're going to be dealing with unit vectors a lot. Now, unit vectors are your buddy once you start shader programming. And if we ever go into any kind of shader programming here on TechArt Talk Live, you'll begin to understand why. All right, but here's where things really get interesting. If you want to get a normalized vector is where you take the length or the magnitude of your vector, and then you divide it through all the components. And so it's really, you take the x component divided by the length, the y component divided by the length, and the z component divided by the length. What you do is that gives you a normalized vector. All right. Now what I did was I went ahead and normalized vector A here. And I got rid of the original vector A so that we wouldn't be able to see it. But you'll see that it really extended just a little bit. It changed its position just a wee bit. I'm going to go ahead and turn on vector A. You'll see that it's almost sitting right on top of it. So there is the vector, there's the normalized A. And there's the original vector. You'll see that because the original length is almost 1, it really doesn't change a whole lot. Other vectors change dramatically. All right, now here we're starting to get into this very interesting. Notice that we haven't done, we did with multiplication of scalar versus a vector, but here's where the juicy part comes in. Okay, we have this thing called a dot product. Okay, now for those of you who are purists and who actually understand linear algebra, this is also called the inner product or the scalar product. And this is done by you add or you multiply the corresponding components of two vectors, ax, bx, ay, and by, az multiplied by bz, but instead of creating brand new components, you add them all together. So the result of a dot product is not a new vector, it is a floating point value. That means it has, yeah, it's a floating point, it's got a dot in it. Exactly. And so that's an important thing to remember. If you ever see vector A times vector B and the result is a float, you know it is a dot product. Okay, for the longest time when I was in my TechArt career, I never realized, okay, great, dot product, cool. What does it do? Well, actually, dot products are super duper important. All right, when they're used for projection, suppose you've got two vectors. You've got vector A and vector B, and you want to see what is the proportion of vector A onto vector B? So basically you're projecting vector A onto vector B. You want to see how much of the length vector A is onto vector B. Well, you do the dot product of them. When you do the dot product, you realize, oh, okay, A is not quite the full length of vector B, so it looks like it's almost like half. So somewhere around there. So that will give you the projected value of one vector onto another. And the dot product is also super important in understanding angles. You say, angles? What in goony goo goes? Suppose that if you have any two vectors in space, they have, it's hard to say because a vector is n-dimensional. But in reality, any two vectors have an angle going off in between them. You use the dot product in order to figure that out. And so you've got right here, you've got this angle between these two vectors, and that is often called as the value of theta. Now, the proof of this angle theory is a little bit abstract and we really don't have time for it today, but if somebody really wants to go into it, I suggest they come and study tech art with me over at FIA, or we'll have some kind of extra curriculum class because this is going to take some time to get into. But yes, any two angles, if they are of the same dimensional magnitude, they do have an angle between them. And so let's take a look. We'll see what that looks like. I'm going to get rid of these two. All right, so we have the dot product. And so we have vector A and vector B. And sorry, in order to produce the angle, I've got to subtract these two. So we have A minus B. But notice here that it says that the A dot product B is 0.4627. So that means if you were to project, let's go from the top view. If you were to project vector A, which is magenta, onto vector B, which is yellow, if you were to project it onto here, you would see that it would take up about 0.4627 of the overall length of vector B. Okay, very, very useful, especially when dealing with things such as computing the amount of diffuse light hitting an object when you are using diffuse lighting. Okay, and the angle between them, and as you can see, these two are kind of like pointing off in wanky directions, but if you were to look at both of these angles orthogonally, they would actually share an angle between them that, according to this, it says angle equals 70.8. So it's about 71 degrees in between these two. Okay, so that is what a dot product is used for. So it is super, super valuable. Okay, now there's this other thing. We say, okay, well, what happens if you want to take two vectors and you want to end up with a third vector? Well, then that is called a cross product. Now, this only works in 3-space, so X, Y, Z, or if you're doing cross products of colors, red, green, and blue. So when you go and you follow this formula, and this is a little bit of a nutty formula, but the first value, the first component is AY times BZ minus AZ times BY. The second component is AZ times BX minus AX times BZ. And the third component is AX times BY minus AY times BX. When you create that, what that does is it creates a resulting vector that is orthogonal to both A and B. What does orthogonal mean? That means it's perpendicular to both. Now this is really cool because when you want to try to figure out, okay, let's get one angle or one vector and we got another vector, and now what is the perpendicular vector for that? Let's take a look at to see what that looks like in Houdini. All right, so I'm going to take the dot product of, we've got vector A and vector B. So let's see, if we were to take A and cross it over to B, we would end up with a dot product that ends up in somewhere in that direction. So let's see what this looks like. We have the cross product. Come on. Ah, there we go. Okay, we have vector A, which is magenta, vector B, which is yellow, and vector A times B, which is the cross product, is going off in that direction. Now, mind you that this cross product is just perpendicular to both A and B. Its magnitude kind of goes off scale, but that's okay. We're not really worried about magnitude. We just know that A and B are going off in that direction. All right, so this is really cool. Once, kind of like division or kind of like subtraction, it is not commutative, meaning it doesn't go in both directions. So we took vector A and crossed it over to vector B, and then we got vector C. Now, what if we wanted to go and do it the other direction? What we would get is the kind of the inverse. So here it is, we took vector B and then cross it over to vector A, and we got a similar vector that we created before, but it's going in the exact opposite direction. Now, you would say like, okay, cross products, what is this really good for? Well, this is really good for when dealing with visual effects and when you're dealing with rigging, because rigging is all about rotating one vector, which is called a joint, towards another vector, and then knowing where the rotational pivot is happening, which is the cross product. So cross products are really important when you're dealing with rigging. So all you riggers, learn your cross products. All right, so what this all gets onto is matrices. I want to kind of like blast through this a little bit because matrices are really just kind of like an n-dimensional array of numbers. Now, typically, it's a number that is 2 dimensions. Now, you can have 3 dimensions if you want, but it's typically 2 dimensions. And here an example of some matrices. We've got matrix A, matrix B. Here, this goes this way. These are all valid matrices. And this is called a 1 by 1 matrix. This is a 1 by 3. This is a 3 by 1. This is 2 by 3. And this is a 3 by 2. This is a 3 by 3 matrix. Typically, it's rows versus columns. So when you say it's 1 by 1, or 3 by 2, that means it's 3 rows versus 2 columns. Now, when you're doing scalar multiplication, so if we have this scalar value, and we multiplied this matrix, we just take this scalar and then multiply it by every one of these components here. Okay, well, that kind of makes sense. It's kind of like a vector. Now, if you want to do addition, you do the same thing as you're doing with vectors. Remember that matrices are really just kind of like vectors on steroids, vectors in multiple dimensions. And so the addition is kind of the same. And likewise, subtraction is also done in a very similar manner. You just subtract corresponding values, and then you get your subtracted value. Now, they do have this weird thing called transposition, and that is where you take a matrix, and then you transform the rows to become columns, and the columns become rows. So if we were to take matrix A and then transpose it, we'd end up with something that looks like this, of where these rows then suddenly become the columns and vice versa. Now, that is good for some situations, especially when you're dealing with rendering. Now, multiplication. This is what you are basically, this is a little bit nutty. So what you're doing is basically taking the dot product of rows and columns to produce components in the corresponding matrix. So what does that mean? Okay, suppose we're going to solve for this component of the matrix. You would grab this row and then do a dot product with this column, and then you'd end up with this value. If you wanted this value, you'd take this row and then dot product with this column, and so forth. And that is where you get the multiplication. Now, this multiplication is kind of dicey, and this is the reason why computers are really good at multiplying matrices. It never goofs up. Now, when I do matrix multiplication by hand, I always goof up. Okay, here is a general rule, is that the number of columns in A must match the number of rows in B. So the result is the rows of A times the column of B. So in other words, if you have a matrix A, which is a 3 by 2 matrix, and matrix B, which is a 2 by 3, well, then you're going to end up with A times B, which is a 3 by 3 matrix. And one kind of rule of thumb that I like to try to do is when you have when you just display the dimensionality of vector A and vector B, if the two inner values here match each other, so 3, 3, then that means that they can multiply each other, and the result is just the outside value. So a 1 by 3 matrix multiplied by a 3 by 1 is a 1 by 1 matrix, and a 2 by 3 multiplied by a 3 by 2 is a 2 by 2 matrix. And the order does matter, because when you take matrix A and multiply it by matrix B, it does not equal B times A. And so it is super important to get the order right. And it is associative, meaning that you can multiply vector A times vector B, and then multiply it by vector C, matrix C, and it means the same thing as A times the matrix mult of B times C. Okay, identity, yeah, that's just a bunch of ones. And here's our example of probably all the identity matrices that you're going to have to deal with. And the zero matrices are, you just take your matrix and then you multiply it all by zeros, and then a zero matrix basically is any zero-packed matrix, which is defined to multiply against A. So you have your identity matrix and your zero matrix. Now, a matrix inversion answers the question, okay, is there a matrix A, and the inversion is denoted by A to the negative 1 power, so that when you multiply the inverse matrix A times A, you get the identity matrix. And it's got to be commutative, so that when you swap them around, do you get the identity matrix? And the answer is yes. And there is a formula for this. Okay, if you were to take a 2 by 2 matrix, you take matrix A, and and then it actually is 1 over the determinant multiplied by the adjunct of A, and you're going, what are those? Well, this is TechArt Lite, and we're crunching in a whole bunch of stuff. The determinant is when you take in this situation, it would be A times D minus C times B, and then you multiply it by the adjunct, which is kind of like this formation here in this matrix. And this ends up with the inversion of a 2 by 2 matrix. Now this kind of extends itself to a matrix of a 3 by 3 matrix. It's really just the same thing expanded to 3 dimensions, and you can see the number of calculations grows exponentially. It's huge. Okay, I'm not going to even bother going into the 4-dimensional one, because the 4-dimensional one takes too much to write. Luckily for us, most matrix operations, when we compute the inverse of a matrix, it's usually done inside of the math libraries for us. Okay, now I know we went over matrices kind of fast, and that is so that next week we can go into really what matrices are great for, and that is for transformations, because that's really the culmination of how we're really using linear algebra inside for computer graphics. And so that's like a introduction of what we're going to be doing next week, and which is an introduction into transformations, and really prepare to have another red pill, blue pill moment, as you would, because when you're dealing with matrices, your mind will get slightly blown. All right. Thank you very much for joining me for TechArt Talk Live today. If you like what you saw, go ahead and subscribe to me on the YouTube channel, and check me out on the Facebook page, and check out Chris Rhoda on the Facebook page and on the LinkedIn. And there's also a page on there for what is it? Oh, I forgot the name of the website. But yeah, go check me out on Facebook and on LinkedIn. All right. Thank you very much for joining me today. And have a great weekend. Have a great week. And I'll see you next week for another episode of TechArt Talk Live.